Hello everyone, my name is Min Shenpan. You can just call me Min. Today I'm going to give a talk about statistical visualization, and it will be a review because we started to add these plots since version 7, but not all in once. So I'm going to give a review of that and talk about a little bit what's new, which Brett probably has covered most of that. So the outline of my talk, right. So the outline of my talk is that, first of all, I will talk about the distribution shape, which is actually a density estimation. And I will talk about distribution fit, and that's actually parameters estimation. Then I will talk about distribution comparison, and in the end, that's something new stuff, the unit integration and data models. Okay, maybe you can make it bigger. Okay, so I'll start from getting the data from example data. That's everyone knows about out-faithful geyser. So this is two-dimensional data. The first dimension is the time eruption, and the second dimension is the height of the eruption. So if I just plot the data in the number line plot, which Brett just showed, that itself can actually give you some information about the density of the data. But if you really want to quantify the location and the density of the data, you want to come here to look at the histogram. And I believe this is not something new to you, so I'll just make it very quick. So the bar is called bins, and each bin have the lower and the upper limits. So I put the data rock in the bottom so you can see the height of the bar is actually the number of the data inside that bar. So that's how you get the histogram. So how to decide the width or the limits of the bar becomes very important. So that's our second argument of the histogram. That's the binning spec. We have many ways to specify the binning spec. You can give a number, width, steps, or just freeform. You can give the cutoffs. That means it doesn't need to be equally spaced. It can be irregular spaced. Of course, it has to take a function. So we make it work. So we just give you the data, and you compute the binning function for that. In this example, it's just very simple, find divisions. We also added support for scaled bins. So you can have log scale, and the way to specify that is just put the log in front of whatever binning method you want to use. So like this. So this is a whiteboard distribution data, and with the log, it's much easier to understand. We also have some named binning spec, which is named after these researchers. I believe it should give you the result quick enough, if I can type. Like, I don't know. Okay. Okay. Yeah, it was. This function was added since version 7, and we, continue to improve the speed. I guess that's what you're talking about, right? And I think so. That's for the binning spec. So how do we want to handle the height of the bar? We have a whole slew of the functions that can apply on the count. So the default, of course, is count, and then you can give the PDF, CDF, survival function, hazard function, cumulative hazard function, and of course a height function. It will give you the binning spec of the whole range. It's not just the bins for each bar. It will give you the whole range. So it will, well, I can just show you. Of course, because I didn't evaluate this one. Sorry about this. Okay. So it'll give you all the bins and all the counts. So you are on your own. You compute the height functions based on this information. And So, and I wrote a height function that actually do the same computation of the PDF that's used internally, and this is the result. Of course, we have scaled height. Just put the log in front of the spec, then it will give you log height. And I want to mention that we also have scaling functions that will scale the visual, not the data. Whenever you put the log in front of the binning spec or of the height spec, it's actually scale the data. But I mean, you know, the height of the counts is scale the counts or scale the bins. But if you use the scaling function, it's actually scale the axis. And since we add the histogram, we understand that people have needs to just get binning information and the count information, and then used not in the visualization, used outside. So we decided to add a histogram list, which has the exactly same spec as histogram. In fact, nowadays, I mean, in modern, you know, like version 8, version 9, all these histogram families start to use histogram list internally to generate the bins and the count. So I'll just skip these because they are all the same. And for two-dimensional data, we have histogram 3D. The only difference between the 3D version and the histogram is that you can specify the binning spec for each dimension, and that will be in a list, the same in the second argument. So for example, I want 20 bins in X and 10 bins on Y, then I can have that. So it's the same thing here. I'll just scan through it. The height functions is the same, it's identical to histogram, which is coming from histogram list. And it is very nice you have a 3D plot that I can rotate if it let me. Okay, but a lot of time, okay, this is slow. So a lot of time you really just want a bird's eye view of the 3D plot. So that's how we decided to add density histogram, which only also take two-dimensional data, but it's just smashed 3D version. Again, it takes the same arguments as histogram and histogram 3D. So I'll just skip it here. The second example shows the density histogram will take the data that actually contains units. And sure.
Have you thought about coloring the three-dimensional bars with those colors?
Yes. That's something I can't cover within 20 minutes. We have a whole bunch of the options for all of these charts. You can, the question you ask is falls through to the color function. So that's actually density histogram is using. So if I put these, well, actually, if I do this, and since I didn't define this one, and it doesn't have frame label, so it will have that, okay? Okay, so now we have seen the non-parametric density estimation that doesn't actually interpret the data. It just draws upon the data. We also have density estimation, which is parametric way that if we want to explain that clearly, I have to talk about smooth kernel distribution first, which is a function that gives you a distribution that based on kernel density estimation. So here again, we have a random data here. And I plot it in the, in the number line plot. This is where the data are located. And I have my kernel function, which I choose to be Gaussian, which is normal distribution. And I choose the bandwidth, which is the standard deviation, to be 0.25. If I put this kernel function located in each data set, each data point here, it will look like here. Okay? And the smooth kernel distribution is a function that gives you the distribution of the summation of this plot. I'll show you here. So here I make a smooth kernel distribution of the same data set, and I choose the bandwidth, which is the standard deviation again, 0.25, and I choose the kernel function to be Gaussian, like I said. And if I plot it, you can see it is actually the summation of this number line plot that I just showed. Okay, so for the later sake, I should evaluate. Oh, maybe not. Okay. So in other words, how do you choose bandwidth, and the kernel function becomes very crucial to the final look. If you choose different bandwidths, you will end up very different results. And so we have a lot of named method for that. I'm not going through the detail. It also takes functions, and these are all well documented. Please go to the documentation to see the specs. And how to choose a kernel function is also important. And here is the one I choose, which is Gaussian, but you can choose something different, and it will give the different results. Okay, so that's a smooth kernel distribution, which is the same kind of role of histogram list in histogram family. And once we have that, I will have the smooth histogram, which is a very useful function that just take the data and do the smooth kernel distribution and then plot the PDF of that. So it's all done behind the scene. So all you need to care about is that put this smooth histogram around the data, and it will give you the PDF of the smooth kernel distribution. And so again, very similar. Smooth histogram will take the same argument as a smooth kernel distribution, which is the bandwidth and the kernel. But they will be in the list in the second argument. Here I choose it to be automatic, which it do something magic to figure it out. And the third argument is like histogram, which will take care of about the height function. And I just put the CDF here. For two-dimensional data, it's the same thing. We can have that. Again, we can put the color functions on top of that. I don't know. Avocado, that's my color. Is that right? Okay. Yep, that's my favorite color. Right. Again, if we want to have a bird's eye view of that, we just smash it and use smooth density histogram. Then we have this. Okay, so once in a while, then you want to know, how your data look like comparing to another set of data, or comparing to some non-distribution, or compare to some empirical distribution of another set of data. Then you want to use then you want to come here to look at probability plot, quantile plot, and probability scale plot. And they are a little bit tricky. I hope I can explain that well. So probability plot is actually a plot of CDF of the first data set versus of the CDF of the second data set, or the distribution you want to refer to. So say that I have a data set, which is empirical, and I have another reference data. And here is probability plot. And I want to show you how is it constructed, so that hopefully we can grasp the idea of that. So I will generate the empirical distribution. This is very nice, very handy tool of the data. Then I use the CDF to get the CDF function for that. The same thing, go to the reference data. And I'm going to ask what's the cumulative probability at a certain data point. So this is my CDF function. I will apply to the data point. And I will apply my reference CDF function to the same data point. So if these two CDF are identical, then if I plot it in this plot, I should get a straight line because these CDF are identical. But of course, they are not. So I'll get a data like this. And they should look exactly like that. So that's the idea of probability plot. Those are, they are comparing the CDF. Okay, and then quantile plot, very similar to probability plot. Quantity plot is also called QQ plot. It's actually the inverse CDF versus inverse CDF. And the inverse CDF is called quantiles. That's why it got the name. And what is quantile mean? It is just reversed and inverse CDF. So I'm asking what's the value or data. And this could be interpolated at a certain cumulative probability. So this is quantile plot. And I'm going to do the same thing here. I will get the inverse CDF for the data and also for the reference data. I'm going to ask what's the data point at certain cumulative probability. And probability CDF, the domain of CDF is from 0 to 1. So here I get 1,000 data points. So they are interpolated. And if I plot these, okay, so they should look exactly the same with my plot. So that's quantile plot. Then probability scale plot is quantile plot with spatial scaled axes. So here, and why do we need this? Because a lot of times the data are heavy tailed. For example, like Weibull distribution. It's heavy tailed, and if I just plot this data inside the quantile plot, here I didn't use the reference data. I use a symbolic distribution with unknown variables here. And quantile plot will do a good job to estimate these variables. That's why this set of functions are called parameters estimation. Okay, this is how I plot it, but it doesn't look like, you don't know that if this is a good fit because it is heavy-tailed. So solution for that is you use probability scale plot and tell it that I'm guessing this is Weibull distribution. So the axes were scaled by the Weibull functions. So then it is actually a very good fit. We have many different scaling functions on the second argument, and we have these, and they are all documented. Okay, now comes to the easier part that we want to compare distributions. For non-parametric ways, we have paired histogram. They are just histogram, so they take the same options, same arguments, the binding method and height functions as histogram. But the left is the left data set, right is the right data set. It will compare it for you, or compare it yourself. But that's just for side-by-side comparison. It could have multiple data sets there. I just didn't show. We also have box Whisker chart, which I'm going to trying to tell you what it is. So here is my data point. Okay, and this is a horizontal one box Whisker chart, and it has a box has whiskers, and the left or the bottom side of the box is the first quartile, which is 25% quantile. And the right-hand side is the third quartile, which is 75% of quantile. And then this is the outlier. This is the far outlier. This is cutoff of the outlier. And that is the third quartile plus 1.5 IQR. IQR is interquartile range, which I showed here. So box Whisker chart doesn't do any processing on the data. It just gives you some statistical measures. Yes?
So will box Whisker chart will also survive the 1 million record test?
Yes, I believe they will perform better, I think. Yes. So, and here I just show you that how to use box Whisker chart to compare 3 different distributions. 2 of them are heavy-tailed, as you can see here, and they have a lot of outliers. So that's non-parametric way. And for parametric way, we have paired smooth histogram, just like smooth histogram, but paired. And we have distribution chart. This distribution chart is actually using smooth histogram to find the shapes. But instead of once, it did twice. So it get the shape on both sides and form a shape like this. You probably will know that for violin plot. So that's how it code. So that's what we have for comparison. Okay, the last part is the data models, and that we have some new data models. One is weighted data. Histogram, we'll just take it without any problem. So before, without weighted data, they are the counts. With the weighted data, the counts doesn't really make that much sense, but we decided to construct the weighted count back from the PDF of that. So you will have these fractions of the count. But if you, well, histogram list will accept that as well. So, but if you calculate the total part of this count, you still get 100. So that's still correct. Of course, it will work. It work with all the binning method and the height functions. Whisker Chart is also working on that. So I'm just browsing through that. All of these statistical visualization will work on this model data. We also have event data. Event data is just, it can have many stuff inside, can have censored, can have truncated. It will also work here. I just take an example from documentation. I'm lazy here. That it cut off the data after it is greater than 4. But you still see it is presenting on the column of 5 because histogram is left closed, right opened. So the fault is still there. Okay. Whisker chart, distribution chart, they all work like that. So as Brett mentioned, time series data in statistical visualization will just throw away these timed stamps and then just render the data fine. Okay, the last one is the wrappers. We introduced wrappers in version 7. We have many nice wrappers. It can be dynamic wrappers. It can be style wrapper. It can be legended wrapper. Now they will all work coupled with the data model. So I'm just showing smooth histogram here, but they should all work across the board. Okay, so that concludes my presentation. Any questions?